So 10.3 in your book, the last thing we are talking about in chapter 10 is something called match pair. We've done match pair before, but in chapter 4, match pair it had to do with how we designed experiments. Well, the inference means hypothesis tests. So anytime you see the word inference in this class, it's referring to two things. It's referring to confidence intervals and hypothesis tests. Okay, so that's the word. If you see inference, that's what it refers to. Okay, with match pair. So it's a special type of T. It's always T. This is always T. So if it's match pair, it's always going to be T. Okay. Okay, so here's the thing. With match pair, we only care about the differences. So I do have two samples, but in reality, there's only one sample, and it's the differences. Okay? So it's one sample with the differences in the two samples. It's kind of difficult to understand, but once you see it, it'll make more sense. Okay? So the reason it's in two sample chapter is because there are two samples, but it's really, when we actually do the test, it's a one sample test. Okay, so when you run this test, it's going to be a one sample, either t-test or t-interval. Okay, it's a little confusing because why is it in this chapter? Everything's been two sample. Why is it one sample? I'm going to explain. There are two samples, but I'm going to explain. Okay. Okay, so nothing changed here. We're good there. Okay. This is the formulas we use. These are the formulas that we use. Okay. So X bar for the differences. So the sample mean of the differences between the two samples. I don't care about the actual numbers in the samples. I just want the differences. Okay. So when I talk about X bar differences, the average difference between all of them. Okay. Same thing. Standard deviation is the difference, the number of differences there are between two. Okay, so on the calculator, we're just going to do t-test or t-interval, with the differences being the only thing we use. Okay. All right. And then for a test, we use this. So the hypothesis, the null is always the differences. There are no differences. It's the same. And then our alternative is no, greater than 0, less than 0, not 0. And then here is our t. Okay. 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 So let's go into what the difference is between the ones we've seen and the ones now. Okay. So we're not going to actually do these tests or intervals. We're just going to figure out which one is it. Is it the one? Is it what test is that we would use, right? Because if you go all the way to the last page, you don't have to go there, but this is every test and every interval we've done. Chapter 8, chapter 9, chapter 10. This is every test and interval we've done. Okay. This is the last one we're going to do. So the question for those is, which one is it? Okay, so look at the first example. Which one would we use to solve that question? Which one of these guys would we use to solve that question? So look at the first example. It talks about, what does it talk about? He randomly selects 50 students. Which one of these would we use to solve that? So you're not looking at this page. You're looking at this page here. But I was just showing you the options. Your options, so do A. Read A. Which inference procedure would we use? Okay. I'm waiting for everyone else. You're one person. So write it down. You don't want to write it down. Write it down. Which one do you use? Write it down. Which one do you use? Okay. You don't have to say. Just write it down, and we'll talk about it. Do the same thing for B. Starts the same. He takes 50 students and has half of them perform. Which one would we use for that one? I'll give you a hint. They're different answers. And I'll explain why. But just A and B are different answers. We're going to use different ones for each. Okay, so let's look at it. First one, he randomly selects 50 students, and each student performs a memory test. Okay, so let's go over the question. The question is, which situation requires a two-sample T procedure? Two-sample T procedure means test or interval. And which requires matched pairs, the one we're going to do today. So we're looking for differences here. A researcher wishes to determine whether listening to music affects student performance on memory tests. So that's the question they have. They want to see, does listening to music positively or negatively affect students' performance on a memory test? Memory test is that game you guys played, when you guys were little, where you turn over the cards and you try to match the cards, right? So they're all facing back, and then you choose, and then that's memory. Okay, if you didn't know that, that's the memory test, the memory game. Okay, so A, he randomly selects 50 students and has each student perform a memory test, once while listening to music and once without listening to music. Okay, he then compares the two scores for each student with music versus without music. Okay, that's the first one. The second one, he takes 50 students. Half of them perform a memory test without listening to music, and the other half perform memory test while listening to music. He then obtains the means and standard deviations of the with music and the without music, and that's what he uses. Okay? So if both of these have different answers, my question is, which one is the two sample and which one is not the two sample? Which one is the two sample and which one is not? Because they don't have the same answer.
Two samples T, right?
Yes, that you are correct. This is the two sample T. We would use a two sample t-test, like we've been using, right? Like we used in 10.2. Good. How is A different?
Because you're comparing it to students while
There you go. Both of those answers combined. B, how many samples are there? Are they the same sample? Nope, they're completely different students doing completely different things. Sample 1 is without music doing the test. Sample 2 is without while listening to music while doing the test. Sample question A. Is question A one sample or two samples? One sample, one population, right? You're not breaking up the 50 kids. 50 kids are the sample, right? One population, right? These guys down here, this population is performing a memory test without listening to music. This population over here is doing a memory test while listening to music. They do both. And then you compare them afterwards. It's a before and after test, right? So for A, we're going to do what we do today. We're going to do what's called matched pair t-test. Matched pair t-test. Matched pair t-test. Okay? That's the difference. Subtle differences. For that reason, you're going to see a lot of matched pair. There's always a matched pair t-test, more than likely on the AP test, because they want to know if you know the difference. They want to know if you know the difference. They always either put a matched pair t-test or a two-sample t-test because they want to know if you know the difference. Okay, so there's always one or the other, right? All right, so let's look at the next one now. Same thing. I'll give you a few minutes. Read it. Which one is the two sample and which one is not the two sample? Okay. Okay, so manufacturer has designed athletic footwear, which it hopes will improve the performance of athletes who run a 100-meter sprint. Okay. 30 athletes are selected for this study. One group of 15 runs the sprint wearing the new footwear. The other half 15 runs with their normal footwear. He compares the mean sprint times between the two groups. Question B. 30 students are selected. Each of them runs one sprint wearing the new footwear and also one sprint wearing the old footwear, their normal footwear. Randomization, flipping a coin for each athlete, determines which one they do first. The two times for each athlete are compared. So what does A represent? Is A two sample or is it match pair? Two sample, good. Two separate populations. One population wearing the new footwear. The other group did not wear the new footwear, so it's a different population. So this is two sample t-test. Down here, all 30 are one sample, right? So this is going to be matched pair t-test. Okay, that's the differences. On a test, you're going to see both of them mixed in together. So you have to be able to tell, because what happens if you get question A on a test and you do matched pair, or you do get question B on a test and you do two sample t-test? What out of 7 points, how many are you going to get? 0. None of them have any of the same parts, right? Population parameter for a two sample has 2 populations. Match pair has 1 population, and they don't say the same thing. You don't use the same formula. The conditions are the same, but you didn't check them, so you wouldn't get any points. There's a big difference between conclusions. Calculations aren't the same, so be careful. Be careful when you're doing that. Okay, be careful and make sure you're using the right test or interval. Okay, so some tips on how to use match pair. Warning, this is not a complete list, so just some tips. The two sets of data must have the same number of elements, right? So if you have we've seen questions, right? We've seen questions before. The question I think you did on the FRQ, the practice FRQ yesterday, one group had 110, one group had 100. Can't be matched pair if they're not the same, okay? So that's one way to kind of tick it off the list. Now, that doesn't mean everything that's the same is match pair. It could also be this one right here, like A, there was 15 and 15, but it was two sample. So it's just kind of, that's one of the things to look for. However, just because both sets of data have the same count does not necessarily make it match pair, so be careful. Is each pair of numbers linked somehow? Sometimes this is very difficult to determine. So each pair of numbers, talking about the data, not the sample size, but the data. And when we do a problem, I'll tell you what that means there. Okay. Okay, so 1 and 2, which one is it? Let's do one more. I've given you 6 examples because that's the most important thing. If you can't tell which one it is, you're not going to get any points. So you have to be able to tell what the difference is. Okay, so 1 and 2. Tell me which test would you use? Okay, so example number 1, Mrs. Donald wants to know if the homework load is different in the English and mathematics department at Westward High School. She randomly selects 24 students. 12 record the number of hours they spend during the semester on English homework, and the other 12 record the number of hours they spend during the semester on math homework. Is there evidence at the 5% level that students spend more time on math on average than English homework? Okay. Example number 2, Mrs. Donald wants to know if the homework load is different in the English and mathematics department at Westward High School. She randomly selects 12 students who agree to record the number of hours they spend on homework in the 2 disciplines, English and math, for the semester. Is there a difference at the 5% level of significance that students spend more time on math homework on average than English homework? So, number 1, 2 sample or match pair? 2 sample, because there's 2 separate samples. Good. 2 sample. We would use a 2 sample t-test like we did in 10.2, the last set of notes. Example number 2. How many samples are there in example number 2? 1 sample of 12. They're doing multiple things. If your 1 sample is doing multiple things, that's usually match pair. So if I'm doing a match pair, what data do I care about? What's the only data that I care about if I was doing the test? That's all I care about, the differences. Do I care how many minutes they spend on homework? No. I only care about the difference in minutes. So if you don't give me a list of how much each of the 12 students spent on math or English, I don't care as long as you give me the differences. Okay? That's all I care about. With example number 1, I do care. I want those numbers, right? I want both lists. That's the difference between the 2. Okay? All right, so let's do one from beginning to end. This is a interval, confidence interval. Okay. So, is caffeine addiction real? Suppose we are interested in the symptoms of caffeine withdrawal. We want to study whether individuals deprived of caffeine exhibit more headaches. We recruit 10 individuals willing to participate in our experiment. Each subject was barred from consuming coffee, cola, and other substances containing caffeine for the duration of our experiment. During one 2-day period, subjects took capsules containing their usual caffeine intake. During another 2-day period, the subjects received placebo pills. We randomized the order in which the subjects took the pills. So they didn't know which one they were getting first, which one they were getting second. At the end of each 2-day period, we had the subjects record their headache level. So a 1 means they didn't have a headache, no headache at all at the end of those 2 days. A 10 is the worst headache they've ever had after those 2 days. Okay? So we have a list of those 10, right? These subjects here are the same people who did both. So they did both, right? So for example, the first person after the 2 days of their getting caffeine pills. So we didn't change. The thing is, they didn't change their caffeine intake. When they took these pills, they took the same amount of caffeine. So they should have no headache, right? But if you look, some of them had some headaches. Okay? Person had a 3 out of 10. A little headache, but nothing major. When they took the placebo, their headache level went up a little bit. Still no really headache, right? But just a little bit higher. Same thing this person. This person had the same after each one, and so on and so forth, right? So what gives this away that it's match pair? What about this makes match pair as opposed to, because I have 2 samples, right? I have headache. Do I have 2 samples? What gives it away that I have once it's a match pair? It's the same sample, and what else? They both received both treatments, and they're measuring before and after, right? So the subjects didn't know which one they were getting first. So they went in both days for 2 days. They gave them their normal caffeine. What's your headache after 2 days? And then they went in for 2 days, gave them a placebo. Looked the same. What's your headache after those? Okay. So if caffeine withdrawal is real, which one should be higher? Placebo should be higher. Placebo numbers should be higher because we expect higher headaches, more intense headaches if you don't have your withdrawal, if you don't have your caffeine, normal caffeine. Okay? So do the data from the study provide evidence at the 5% level that caffeine withdrawal is a real phenomenon? That's what we have to do first. So we're going to do A first. Okay? So let me, oops. Okay, so population parameter. You said we had 2 samples. So let's go back to the start. Only one population parameter. We always start mu of D. Mu of D. D for difference, because that's all we care about with one sample or with match pair. Okay. Equals true mean difference Okay, and how do I explain? Well, before I did this, it's easier if you kind of preload yourself. What I mean by preload is when we start crunching numbers, when we start doing calculations, when we start doing all of that stuff, which numbers are we going to use here? I have a lot of different numbers. I have 3 columns of numbers. Which ones are we going to use? There you go. We're not going to use any of these numbers. This table is meaningless to us. It doesn't help us right now. It doesn't help us until we make another column. So I'm going to make another column, either to the right or to the left. It doesn't matter where. That column is going to be caffeine minus placebo. Caffeine minus placebo. Okay, so doesn't matter where you do it. I just need another column because currently the information is useless to me. I need the differences. So I'm going to say caffeine minus placebo. C minus P. Okay? So the first person, 3 minus 4, is a -1. So what does a -1 score mean? It increased, right? In terms of our question, is a negative number going to help prove or help? What is it going to help us do? It's going to help us, it's going to help us reject the null hypothesis. It's going to make us say, hey, there is something going on here. If we can reject the null hypothesis, that means there is something going on here. Caffeine withdrawal is real. Okay. Okay, next one, 0. Next one is -4. Next one is -1. Next one is 0. Next one is +2. So they actually had a higher, wait, -2. Sorry, -2. Went the wrong way. -3, -2, 0, and -1. Now, this is what I always do afterwards. Once I do that, this is what I do. Why do I do that? Because it doesn't confuse me. I don't need it, and too many numbers sometimes can be confusing. Okay? We don't need that for this one. We're not doing a 2 sample. Okay? You don't have to do that, but I always do that when I'm doing these because otherwise it confuses me. Oh, what number do I use again? Okay? So now let's come up with X bar for C minus P. And let's come up with standard deviation for C minus P. Actually, I shouldn't use C minus P. I'm going to use D because they use the letter D. It's the same thing. D is difference, but they use D. So I'm going to use D as well. So I'll say this is D. Okay, so let's put those numbers in L1. Pause all the zeros and negative numbers. Negative 1.4.
This was you a couple weeks ago.
Okay, so what do we got? Negative 1. When you're putting numbers in, make sure you use negatives instead of minuses. In real life, negatives and minuses are the same thing, right? But to the calculator, they're very different things. Yeah, because I think I've done that before, and it'll give you an error, and you're like, what did I do? You didn't do anything wrong. According to the calculator, you did, but in real life, you didn't. So just be careful with that. Negative 2, 0, negative 1, negative 2, 0, negative 1. Should be 10 numbers, and yes, I have 10 numbers. Okay. So let me catch up. You guys are probably already past me. Let me catch up real quick. So my number's in L1. So negative 1.4, mean difference. The average difference for all 10 of these people is negative 1.4. So caffeine. So out of these guys, the average headache went up for placebo. And then S of X is 1.350. Yeah, 50. Okay, good. Okay, so let's go back to this. Okay, so now that we know that, the reason I did that before is because X bar is a part of, X bar D is a part of mu D, right? It's the sample from that. So who does mu D represent? For all of these numbers, these are just 10 people, right? Mu D means every number that exists from everybody. Okay, that's what that means. So the true mean difference between or in. So what are the differences between the two groups? Not numbers wise, but just in plain English. Like what are the differences in the two groups? Headache levels.
For people taking caffeine pills and placebo pills.
There you go. Difference in headache levels for people taking or consuming caffeine or taking caffeine, however you want to pronounce that. I think that's how you spell caffeine. Yep. And those who do not. Okay. All right. It's a one sample. Oh, so let's do hypotheses. Hypotheses. For these guys, your null will always be the true difference is 0. There is no difference between the two. There is no difference between the two. That's going to be that guy. This over here will be greater than, less than, not equal to. So if we're trying to show that caffeine is a real thing, caffeine dependence or caffeine withdrawal is a real thing, which one is ours going to be? Less than, yeah. We think P is going to be a bigger number than C. We think these guys over here will have higher numbers than these guys over here. So we think C minus P is going to be a negative number. Less than. Okay. Alpha level 0.05. Okay. Okay. Next one is conditions. We only have to check one because there's only one group. There's not two groups like in the two sample. SRS, 10% condition. Okay, so SRS. Was this simple random sample taken? They recruited 10 individuals. Recruiting is not the same as, yeah, recruiting is not the same as SRS, right? It's actually the opposite of SRS. Recruiting means you pick them. If I recruit you, that means I want you there, right? Random is not. So that's not, so it doesn't fulfill SRS, but what can we put instead? Yes. We could put random assignment. We could put subjects recruited. But you can just put RA, or you could put random assignment. Is done. Okay. 10% condition and is less than 10% of big N. So little n, there were 10 subjects. Less than 10% of. There you go. Well, it's only going to refer to the people who actually consume caffeine, right? So all caffeine users, all caffeine people, all caffeine, whatever you want to say. Okay. And 3, normality. So you're never going to have number 1. If you're never going to have a situation where you can use number 1, it's stated. For these, they will never tell you that. Okay, because it's differences, not the actual numbers we're using. So we're only going to say our sample size is big enough, or we have no outliers on a box plot or a dot plot. So I think we're going to have to use that one there. Okay. So since n is less than 30, let's go to our calculators. Yeah, it's a very funky looking box plot. No outliers.
I mean, yeah.
But there is definitely some skewness. So why does it have no arm? Left arm is gone, right? Why does it have no whisker, or arm, whatever you want to call it? Exactly. All the values are negative, right? All the values are negative. So So 25% of the data is here. 25% of the data is in this one here. 25% is in here. Where's the other 25%? It's right here on the line. 25% of the data is at 0. And go count the numbers. How many zeros did we have on our list? It's about 25%, right? So it's not going to be 25, 25, 25, or will it be? What is 25 divided by 10? It's 4, right? So it's close. That's why. So 25% of the data is right on 0. 25 is here. 25 is here, and then 25 is here. Or, yep. Okay. So still no outliers, right? No outliers present. Okay. There is some skewness, but we just mainly care about the outlier. Without that, this part right here, that's pretty balanced, right?
Yeah.
So, I mean, you know, even though there is some skewness, I'm not going to lie and say there's no skewness. There is some skewness, but really we're just concerned about outliers. As long as you note the outliers.
Left or right?
That's a good question. So would it be skewed left or right?
Skewed to the right.
So we have a lot of data here. We have 25% here, right? And 25% here. So 50% is over here in this smaller area, right? So it would be skewed to the left. Skew to the left.
So you would fall to the
Yep, you would fall to the left. You would ski left. You would, however you want to think about it. Exactly. Which way would you, I think about skiing. You'd rather ski left than right, because if you ski right, you'd fall off the cliff. That's not really called skiing. That's called dying. Okay.
lot of experience in Skyrim.
All right.
You can honestly climb up like that. Because you're only shot yourself off the cliff. It's a classic.
All right. So
What else do we have?
test statistic.
I still- Oh, wait, that's not that hard.
Okay.
X bar D minus 0.
Well, are we doing it? That's for an interval. Are we doing an interval here?
Oh, wait, there's another one? Tortitas. Oh, wait, there's another one?
Right. This one right here. So we have one for a paired confidence interval, and we have one for a paired t-test. So which one are we doing? A test or a confidence interval? We're not doing a confidence. So we're going to use this guy here. We've already done our hypotheses, right? So we don't have to worry about that. Oh, is that what you said? Oh, okay. So xd minus 0, you don't have to write the minus 0 part, because mathematically, if you minus 0, it's always going to stay the same. There's no value where if you subtract 0, it'll change the value. So you don't have to put the minus 0. You can if you want. It's part technically of the formula, but you do not have to. And then what was the bottom? Standard deviation of d over the square root of nd. And then there is a degrees of freedom, right? So we got to, it would be n minus 1.
So the degrees of freedom always go with the test statistic, right?
Yes, I would put it there. Will you get knocked off if you don't have it? No, but you need to include it in your calculations. So somewhere in your calculations, you have to have the number, either the calculator number or the our approximation. I always do it there just so that when I'm doing my calculations, I always remember to include that. But you don't have, it's not required. Okay, so calculations. Okay. So we have t equals, so we're going to have, since it's a test, we always have to draw a picture. What number is going to go in the middle? 0. T equals, what was our average? Negative 1.4?
Yeah.
That was our average difference. And standard deviation was 1 point something.
1.35.
And then square root of 10, right?
Yep. Squared.
That's squared?
Is it squared?
What did I say squared?
That's not squared. That's yellow.
Yeah, that's for 2 sample.
Yes, so.
Okay. Okay, so what number here for my shading part? Which number am I going to graph? Negative 1.4. And I'm going to shade which way? Less than, right? We chose less than. Less than is to the left.
Sleep's important, guys. I know. I like it.
Okay. Calculator time.
Yes.
When you use a calculator, if you're going to use a test, the test function on the calculator, make sure you use a t-test, 1 sample t-test. It's not a 2 sample. So it's going to be number 2. Data. So what's the claim here? What do we put for the claim? 0. L1 is where my data is. Frequency, just leave it as 1. We chose less than, no. Less than?
It's supposed to be negative, right?
Yes. Okay. Calculate. Okay. So write down the p-value. P-value is very small. The t-score, which is negative 3.28. And then degrees of freedom is not written there, so just put degrees of freedom equals 9. And that's all we need. Everything else we have. X bar, S, N, we have those from earlier. Okay, conclusion. We use the same conclusion, same sentence frame as we did for one sample t-test. Okay, so we compare p-value since p-value 0.0048 is less than alpha 0.05. We reject the null hypothesis. Okay. Therefore, we have sufficient or significant evidence to show, how do we word this? To show what?
Caffeine withdrawal is a real phenomenon.
There you go. Caffeine withdrawal is a real phenomenon because if the differences are less than 0, that means caffeine withdrawal is a real thing. Is a real phenomenon. Boom. Done. Okay. So that was part A. Part B is very similar to that. Part B, if you go back to the question, part B, use a 90% confidence interval. We're using 90% confidence interval, even though we should probably use a 95. We're going to go with what they say. If we want to keep apples to apples, you should use a 95. But since they said 90, we'll go with 90. Use a 90% confidence interval to estimate the true increase in level of headache scores that result from being deprived of caffeine. Note, you do not need to repeat any steps you have completed already. So population parameter, we don't have to do. Assumptions, conditions, we don't have to do. The only things you have to do for this one are calculations, test statistic, conclusion. Okay, do that. Okay, so I get negative 2.183 to negative 0.65 or 6175. Okay, so because we're running out of time, we are 95% confident that the true mean, 90% confident that the true mean, and then you repeat right here, the true mean difference in headache levels for people who have right here Right here, the true mean difference for people who have headache levels for people taking caffeine and those who don't is between negative 2.183 and negative 0.6175, which supports our conclusion of rejecting because 0 is not in the interval. Good.